Hello, my name is Adrian, and I will be presenting our MEC 203 final project. Our project is named Kronos, a 6-wheel Martian exploration rover that we designed and modeled in Fusion 360. Kronos is a 3x3x3 meter rover built to traverse through rough terrain and collect samples from the Martian surface. In this video, we'll talk through our design concept, its subsystems, our motion studies, and how we used fits and tolerances to model a realistic rover. We started by brainstorming a few different ideas for the form of the rover. Our final design was determined for the following reasons. We chose a 6-wheel design as it provided for increased stability and obstacle climbing ability. We chose to affix a 3-degree of freedom arm to enable the rover to collect hard-to-reach samples. For the form of the camera mast, radar dish, and solar panel, we chose our locations in order to prevent interference with each other. Here we have the isometric, front, and side views of our sketch for the 6-wheel rover. The first subsystem we modeled was the mobility system. Kronos has 6 driven wheels with custom tread and internal spokes for stiffness while keeping the mass low. Each wheel mounts to a wheel hub, which then connects into the suspension. The suspension is designed so that all 6 wheels can maintain contact with the ground while climbing over rocks and slopes. This improves traction and reduces the chance of tipping as the rover moves over harsh terrain. The chassis is a rigid, sealed box that acts as the structure of Kronos. It provides side mounting points for the suspension arms, a sloped front panel to improve the approach angle, and flat top surfaces where we attach the arm, solar panel, camera mast, and radar mast. Internally, this is where we imagined the electronics, batteries, and computers would be housed. For sample collection, Kronos uses a 3-segment robotic arm ending in a 2-finger gripper. The arm has a shoulder, elbow, and wrist joint, all modeled as revolute joints with motion limits to avoid self-collision. The arm is mounted on a rotating base on top of the chassis, giving it a wide workspace so that it can reach to the ground in front of the rover and move rocks toward the hypothetical storage area. On the top deck, we added 3 main subsystems. The solar panel, mounted on its own mast, is the primary source of power. The panel can rotate to optimize exposure to sunlight during the mission. The camera mast raises the camera above the body to provide an elevated viewpoint for navigation and inspection. The camera can rotate about a vertical axis and also tilt about a horizontal axis, letting it perform panoramic scans of the environment. The radar dish is mounted on a separate mast at the rear of the rover. This represents the high-gain communication system, which can rotate to align with an orbiter or ground station for data transmission. Our first motion study demonstrates driving motion. We applied a rotational input to one wheel joint and linked the others so that all 6 wheels spin together as the rover translates forward. Unfortunately, Fusion was not able to render both sides of the wheels moving at once, so we had to split the motion study into 2 sides, but both sides drive as intended. This shows how the wheel and suspension design allow Kronos to roll smoothly over uneven ground. The second motion study focuses on the arm deployment. Starting in a stowed position, the shoulder, elbow, and wrist joints rotate to extend the arm out in front of the rover and lower the gripper toward the sample on the surface. The first sequence demonstrates the shoulder and elbow rotations, with the second illustrating how Kronos can interact with its environment and pick up rocks or soil using the wrist and finger joints. Our next 3 motion studies highlight the sensor and communication systems. In this animation, the camera mast rotates to perform a panoramic scan of the surroundings, spinning along the vertical axis and being able to move the camera head along the horizontal. The radar dish swings through a wide angle to seek a communication target, also using the motion styles as the camera for maximum performance in communication. The final motion study showcases the primary energy source, our solar panel. The solar panel adjusts its angle in a single degree of motion along the vertical, representing how the rover could optimize power intake as lighting conditions change. To make Kronos more realistic, we specified fits and tolerances for the key connections. When we connect the suspension to the chassis, we use an H7 P6 locational interference fit. This represents a pressed connection that locks the suspension brackets rigidly to the body so that they can carry high loads without any play. The arm base and arm joints use an H8/F7 closed running clearance fit, which gives the pins a small clearance in the holes. This allows the joint to rotate smoothly while still keeping good positional accuracy. The camera mast and radar mast also rely on the closed running and locational clearance fits, such as H8/F7 and H7/H6, so they can rotate for scanning but remain precisely located on the chassis. For the wheels, we use an H9D9 free-running clearance fit, creating enough clearance for the wheels to suspend freely at higher speeds and over rugged terrain. Meanwhile, the wheel hubs have an H8/F7 closed-running clearance fit attached to the suspension. Finally, the solar panel mount uses a combination of interference and clearance fits. The panel is held firmly to a mast with a locational interference fit, while the mast to chassis connection uses a locational clearance fit to position the panel accurately, but still allows small rotational adjustment to track the sun. In conclusion, Kronos is a 6-wheel exploration rover with functional suspension system, a 3-degree of freedom robotic arm, a camera mast, solar panel, and radar-based communication system, all designed and animated in Fusion 360. Through this project, we practiced going from concept sketches to CAD parts and assemblies to motion studies and tolerance decisions that make the design realistic. Thank you for watching.